analyze kinematics, like me taking off. Position versus time. Now let's calculate the speed as a function of time. Well, what is speed? Speed is the distance traveled, this cell minus the previous cell, divided by the change in time. So this is my speed between these 2 points. At the very beginning, only 14 centimeters per second. And when is that? That's in between these 2 points. So it's halfway between these 2 times. And so I'm going to list the time as the average, AVERAGE, of these 2 points separated by a comma. And so this is time in seconds again. And as we move down, it averages each one of these. And I can now plot my speed as a function of time. Insert chart, XY. There it is. And again, we have the same thing where the speeds are lined up with these numbers instead of the times. So I'm going to do 2 things. One, I'm going to move everything down, and I'm going to add at 0 seconds, I wasn't moving at all, which is pretty evident from the video. And I'm going to add that to this graph. And then I'm going to change the x-axis to this time. So I right-click here, select data, and again, copy this column over, but change it to column A. And now I can see I have time in seconds. I can change the chart title to speed versus time. Now you might ask yourself, why does this look so awful? Why are these so nice and clean and this is so bad? Well, was I really moving super fast and then slowing down? No, I wasn't. I sped up pretty smoothly, but it's because of little errors in these measurements that I took. So I didn't click on the perfect center of mass of my body. And so what you see is here, this speed is artificially a little bit higher than it should be. And as a consequence, this is a little bit lower. So it looks like I actually decreased in speed at this point, which I didn't. And just for the sake of argument, I'd like to add a couple more rows. I'm going to extend this time in tenths of a second. This is equal to the previous column plus 0.1 seconds. And I'll add a couple more of those. And then I'll say, maybe I got up to 5.5 meters per second, but then got kind of tired, 5.75, and I stopped speeding up. And now we can extend these. Now what it looks like now is I started at rest, sped up, and then got going as fast as I could, continued at constant speed for a few tenths of a second. Now we could try to calculate acceleration from velocity by taking the slope of these lines just like we did here, taking the slope of the displacement graph. We take the same function and copy it down here. If we were to graph this, let's put up a chart, insert chart, scatter. It's an absolute mess all over the place, right? Because here we see these data would indicate very high acceleration right here, and then negative acceleration here, and it's all over the place. And the reason it gets worse and worse as we take derivatives is because we're dividing by a tiny time, only 1/10 of a second. So a tiny error here correlates to a rather large error here and prohibitively high for acceleration. So we're not going to do that. We're going to calculate the slope of this line manually by inserting a line, shape line, and I'll just go from here to, let's say, here, before it seems my acceleration dropped off. And so now I manually can see that this is about 1.3 seconds, and this is about 5.3 meters per second equals 5.3 meters per second divided by 1.3 seconds. And so my acceleration in this area is about 4 meters per second squared, about half of gravity. And it would taper off to about 0 if I reach my maximum speed at about 6 meters per second or 13 miles an hour. Okay, what if I wanted to graph my kinetic energy? Because then I could take the slope and that would be my power. So let's just calculate the kinetic energy. It's equal to 1/2 mv squared. 0.5 times my mass, which I could put that here, times v squared. And the only problem is now I have to put a value in here for my mass, and I'm going to say I'm about 70 kilograms. So mass equals 70 kg. Right, and now I can see what my kinetic energy does as I speed up. Oh, that's a problem. Because as I move down, it's moving down from here, and these values are 0. So what do I need to do? I need to put a $ in here so that position doesn't update as I move down. And these kinetic energies would correspond to these speeds, which correspond to these times. So I'm going to take these times. But the problem is I realize when I do that, it's all messed up because these are formulas. This was made to take the average of these two numbers. So rather than have the formulas, I want these exact values pasted down here. So I go back instead and do a paste special and paste just the values. And now I can chart this. Insert chart. And this is my kinetic energy as a function of time. My axis title on the horizontal scale is time in seconds. And this is kinetic energy in joules, right? Because I have kilogram meter squared per second squared is a joule. So I can see I've forgotten to update the time to be in seconds rather than just these numbers. So I'm going to right-click on the chart and select data. And it will tell me. Now I can see how my kinetic energy increases with time, and I know that the slope of this line is a rate of increase of energy, which is the power that I'm putting into my body as I speed up. Let's take the maximum slope first, just to see what my maximum power output is. And that would be, right around in here, around 1 second, is when the rate of change of my kinetic energy is maximum. So we insert a line. This line now represents the maximum slope I get. I can move it over here. That would correspond to about 800 joules in about 0.6 seconds. All right, and so that's at 1 second. So I could say, yeah, at about 1 second, my power is equal to about 800 divided by 0.6, right? Which is 1.3 kilowatts. At that moment, that's how much I'm putting out. And then we could take another one and say, well, how about at the very beginning, my power output is 0, right? Because if this is a straight line, and we square it, it's parabolic, so the slope of that line is 0 at the beginning. But let's say, how about at a quarter second? That would correspond to a gain of 300 joules in 1 second. So that'd be about a quarter second, 300 watts. And then, of course, at the very end, I could see that my power, is 0 if I'm not increasing my speed. And if I started to slow down, my power would be negative. I would be taking kinetic energy away from my body. So rather than graph power over time, I'm just going to say, look, in the very beginning, my power output is 0. And then during the first half second, the power output is on the order of 300 watts. It gets much bigger, a little over a kilowatt at 1 second, and then drops back off again as my speed plateaus. So hopefully we have some idea how to use Logger Pro and take the kinematic information and analyze it to give us speed, kinetic energy, and acceleration. Thanks.